A 3.0 millimeter diameter wire carries a 12 amp current when the electric field is 0.085 volts per meter. What is the wire's conductivity? Well, for this one, let's go ahead and remember that conductivity is the measure of the ability of a conductor to move charge. In this case, the charge carriers being the electrons in the conductor. As usual, I'm going to like to start this with a sketch illustrating our wire and the variables that we have to work with. So we're told that this wire has a certain diameter. The diameter of this wire is 3.0 millimeters. Now, dealing with a wire and dealing with current, we're probably going to need to know the cross-sectional area of this wire. So while we're at it, let's go ahead and figure out the expression for the cross-sectional area. We're going to assume that this wire is cylindrical, and so the cross-sectional area would just be the area of a circle, pi r squared, where the radius is just the diameter divided by 2. This means that the cross-sectional area of our wire is pi times the diameter squared over 4. We're given in this problem the magnitude of the electric field, so we could assume that there is an electric field in this wire due to a difference in potential between the ends of this wire. So I'll illustrate the electric field in the wire with the variable E, and we are given that the magnitude of the electric field is 0.085 volts per meter. This electric field gives the signal to the conduction electrons to begin to move. So the current direction will be in the direction of the electric field. So this is our current direction, I. Now don't forget, the current direction is the direction that positive charge would move. If this wire were a copper wire, our charge carriers are electrons, so they would move opposite the direction of this positive current. We're given that this current is equal to 12 amps. Now, to find the conductivity, we should recognize how we first discovered what conductivity is. Conductivity was given as the proportionality constant between current density and electric field. So current density is directly proportional to the electric field, where the proportionality constant is the conductivity. What that means is the greater the conductivity, the greater the current density. The smaller the conductivity, the smaller the current density. And remember, current density is defined as current per unit area. So there's the area that we thought we were going to need. And that current per unit area is equal to conductivity times electric field. This means that conductivity is equal to the current in our wire divided by the product of the wire's cross-sectional area and the magnitude of the electric field in the wire. Let's take this expression for conductivity and look at it a little bit. Notice this says conductivity can be expressed as the ratio of current to the product of the area and the electric field. In terms of the parameters given in this problem, this means that conductivity is equal to the current divided by the product of the wire's cross-sectional area, which is pi times the diameter squared over 4, times the magnitude of the electric field. Rearranging this, we get conductivity being equal to 4 times the current in the wire over pi times the diameter squared of the wire times the magnitude of the electric field. Let's plug in numbers to see what we get for this. So we have in the numerator 4 times a current of 12 amps. In the denominator, we have pi times the diameter, which is 3.0 times 10 to the minus 3 meters. The diameter is squared, so that quantity is squared, times the magnitude of the electric field, which is 0.085 volts per meter. After doing our unit check and plugging into the calculator, I get a value for conductivity to be 2.0 times 10 to the 7th mhos. And remember, a mho is just a reciprocal ohm meter.